Okay, I think we can start right now. Already 2 minutes past 10 a.m. Okay, thank you for coming for third day of our course. Good day for everyone. I hope we are stay safe and healthy. And Assalamualaikum warahmatullahi wabarakatuh. Today we have Dr. Aditya Gusman from GNS Science, New Zealand. He will talk about volcanic tsunami source mechanism. Before we invite Dr. Gusman, I would like to inform you regarding the assessment of this course as a requirement for the certificate. The first one, I strongly suggest you to fill up the list of attendance. And the second one, we have 3 assignments. And the first one that I have sent you to email yesterday, please fill it up, and it could be our consideration to give you a certificate. If you have any question, please do not hesitate to contact me by email. Thank you. Then, without further ado, I would like to invite Dr. Gusman to give his lecture. Okay, ready? Dr. Gusman?
Okay, I'm ready.
Yeah, sorry. I think we can make a bit rule for our lecture for today. We can break for a while every 30 minutes, and we give time for participants to ask questions and comment. What do you think about that? It's okay?
That's good.
Okay.
For me.
Okay, thank you, Dr. Gusman. Time is yours.
I'm going to share my screen now.
Yes.
Now, yeah, so this talk, in this presentation, I would summarize what scientists in the world have learned from volcanic tsunami events. Okay, just this is about me a little bit. So I was in the same class as Professor Andri and Dr. Zul. I was in the class of 1998 at ITV. And then after I graduate, I continue to get a master degree, also from ITB from 2003 to 2006. And then after that, I went to Japan, to the Institute of Seismology and Volcanology in Hokkaido University. I was there for 7 years, so I did my PhD there for 3 years, from 2007 to 2010, and I was a researcher from 2010 to 2014. After that, I got an opportunity to go to University of Tokyo as a researcher at Earthquake Research Institute. So I was there from 2014 to 2018. And then I got an opportunity to go to New Zealand. So I moved here to New Zealand. So I've been here from 2018. So yes, I don't know what happened next. So I just let them blank here, over here. I have more space. Maybe I can move to other places in the future. I don't know. Okay. Pointer pen. Yeah. So this is an introduction to tsunami. So tsunami is different than ordinary coastal wave. Wave or energy in ordinary coastal wave is limited to surface of the ocean. This energy dissipates as the wave breaks on the shoreline. So, but the energy in tsunami wave affect the entire column of water. from the ocean floor to the surface, not only the surface. You can see here for the ordinary wave, this interaction is just in the surface, but here it's in the water, all the water column. So this energy does not easily dissipate. So instead, water push upward over a large area, and because of long wavelength, when it's reached the coastline, it can travel much further inland. Let me, I don't know. I still cannot really control my, okay, I think I'm good now. Okay, the photograph below shows what happened when a mega tsunami hit the land. So the photo was taken in Lokma after 2004 Indian Ocean tsunami. So this area was destroyed because of the tsunami, and also other countries surrounding the Indian Ocean. And here's some characteristic of tsunami wave. Tsunami can have wavelength ranging from 10 to 500 kilometer and wave period of up to an hour. As a result of their long wave, tsunami act as shallow water wave. Even though it's travel in the deep ocean, it act as a shallow wave because the wavelength is so fast, 500 kilometers, so long. So basically a wave becomes shallow water wave when the wavelength is very large compared to water depth. So here there's an equation, shallow water wave move at speed of c, that is depend on the water depth. From this formula we can see g is just the acceleration of the gravity and h is the water depth. In the deep ocean, typical water depth is about 4 kilometers or 4,000 meters. So a tsunami will travel at around 200 meters per second or 700 kilometers per hour. So as tsunami leave the deep ocean, get inside the shallow water, it transforms. So for example, here the wavelength at 4 kilometers is about 213 kilometers. If tsunami wavelength is 200, if the wavelength is 213 kilometers at that depth, then the wavelength would reduce to only 23 kilometers at water depth of 50 meters. Then tsunami speed, the tsunami speed is of course related to the water depth. So the water depth decreases. So the tsunami basically slows. The tsunami flux, which is dependent of both wave speed and wave height, remain constant basically. So consequently, as tsunami speed become slower, the height grows. This is called shoaling effect. So that's basically why we have not so high tsunami in deep ocean, but high tsunami around the coast. Now, here's from field survey in Banda Aceh. You can see that person over there under the yellow arrow. That was me 16 years ago, somewhere near Banda Aceh, right after the tsunami. I visited that there. Well, this is not after tsunami. It's like 2 months after the tsunami. So usually, right after a tsunami, scientists go to the field for a survey. The purpose of the survey are to observe and document the effect of the tsunami and then collect the data, like including perishable data as soon as possible. Also learn about the nature and the impact of the tsunami. Surveyors are usually encouraged to give recommendation on the need of further research, planning, and preparedness, something like this. You can see this, some researcher from Japan also visited the area, and this guy is from the US. He's from USGS. Here's some destruction photograph of the region. Now, what we we can measure flow depth. One of the parameters that we measure is flow depth. This is how we measure the flow depth. Flow depth is basically measured from the ground level. So the dashed line here is the tsunami level, and inundation height usually measured from the sea level at tsunami arrival. Tsunami inundation height can also measure from mean sea level. So usually we have notes about our measurement, what's our reference. And then run up height, this is at this point at the very end, that it's called run up. And the run up height is measured from that point to the sea level. And this is, we sometimes measure the water height from the watermarks like this. Tsunami left watermarks on the wall. This is outer wall of the house, and this is inner wall of the house. We can see watermarks outside and inside. We may measure at multiple places at this house. So just for example, the flow depth above the floor is about 70 centimeter, and flow depth above the ground is 75 centimeter. And this distance from the coast is 220 meter. And then we can also find out the ground level, which in this case is 1.1 meter. For the ground level, we could use DEM, in this case, we use LiDAR, so high frequency data. I mean, high quality data of LiDAR. So the tsunami height from mean sea level was 1.85 meter for this event. So, well, this is for Palu. So I know this is about volcanic tsunami, but fortunately I didn't go there because lack of fun. So I visited Palu, and then I think a couple months later, there's another tsunami in Sunda Strait from the Anak Krakatau event. I couldn't go there, but basically what I want to show you is how we measure flow depth here. So this is some 300 data points that we collected in Palu. So we just plotted the height above the ground or height above mean sea level and plotted the points on a map like this. So this one was collected by Abdul Mohari. So this is published in his paper. So they went to, so there was a tsunami on December 22nd, 2018. So the tsunami was generated by volcanic eruption of Anak Krakatau. So in this paper, Muhari described result of post-tsunami field survey. They conducted the survey 4 days after the tsunami. So the survey team basically measured tsunami run-ups and other impacts. Yeah, and then this is the plot for their measurement. So you can see tsunami height on the x-axis here, and then this is the map where the point of measurement was taken. Now, the other way to measure tsunami is use instrumentation. So here, this picture from Satake 2015 summarized different kind of measurement, different kind of instrument used to measure tsunami. So at the harbor, usually we have tide gauge. It could be measured in acoustic waves or pressure gauge. And then little offshore, like at depth of 100, 200 meter, we have offshore tsunami measurement usually using pressure gauge. And then we also have deep ocean measurement at depth of down to 6 kilometers. So this is usually using quartz crystal pressure gauge. And precision can be 1 centimeter for this bottom pressure, high precision pressure gauge. So this is pressure gauge developed by NOAA. It's called DART system. So when an earthquake happened, this dart was triggered. So the pressure record the water level and then send the data using acoustic to the buoy, and the buoy send the data to the ground station through the through satellite. Okay, and now some definition for amplitude of wave. So just maximum amplitude is from 0 to the peak, usually positive peak. That's the crest. Or we can also calculate the trough or the negative peak. The wave height also refer of the range of the amplitudes of the peak and trough. Crest and trough. And usually in the record, this is a record from Maldives. So here is the tide, and on top of the tide we have the tsunami wave. For a more clear view of the waveform, we usually remove the tide, so we get only the tsunami waveform. This is another example from Phuket, Thailand. So in this case, the leading wave is negative. So I have leading negative wave. This is the arrival time for the Maldives. This is the leading positive wave. So this is for the case of 2004 Sumatra Andaman earthquake. Again, this is an example from an earthquake, not from a volcanic event, but this is what tsunami look like. So what I want to show here, actually a recording of tsunami coming and the tide gauge record. Unfortunately, we do have videos of the Anak Krakatau event, but in those videos, so many victims captured in the video, I don't think it's appropriate to show them here. And we do also have tide gauge record, but the tide gauge record was not exactly where the video was taken. So, but this case, in this slide, I have the video in Miyako City, which is about 150 kilometers away from the epicenter. And also I have the tide gauge record at that city. So Miyako, you can see the duration of the wave. So the first cycle of the wave, well, it's about half an hour. So it's a long time. So obviously this is from earthquake, and the duration or earthquake period from earthquake source is longer than tsunami wave period from earthquake source is much longer than tsunami period from volcanic event usually. But yeah, this is how tsunami might look like. Large tsunami might look like. So it came slowly. So here we have breakwater, and you can see the boat are still there, but soon it was dragged by the tsunami current. So the current is so strong. I bet it was anchored, but the tsunami was too strong, so it bring the boat to the direction of the tsunami. And we can see here the breakwater. It was high, but was not high enough to block the tsunami, because this is a huge tsunami in 2011 in Japan. I'm just going to skip this, and then we can see finally the tsunami overtop the wall, and then after that it's just unstoppable basically. Like the houses over here was destroyed, and the cars were pushed by the tsunami. Some of the wooden houses was destroyed. And then you can see here the blue line here is a simulation, and the red line here is the tide gauge record. So you can see the record was stopped here because the tsunami destroyed the station. So, but fortunately, the data was recorded. It was sent in real time. So the probably power was cut off after this at this time. So the station was not sending the data any longer. Yeah, you can see here also from the comparison, this show that we actually can simulate the tsunami quite accurately. Now, yeah, so from tsunami, I mean, this course is about volcano, but from tsunami perspective, volcano is only 5% of tsunami source. So other sources, the vast majority of the tsunami sources are from earthquakes. 72% of tsunami sources are earthquakes, and only 5% are volcanic activity. So here's just schematic from Anak Krakatau tsunami. So, but this Anak Krakatau eruption, the flank, one of the southern flank of the Anak Krakatau collapsed, and that's what generated the tsunami. And then here's the other type of tsunami source was landslide. Okay, here's an animation of tsunami generation and propagation because of an earthquake. As I mentioned, tsunami can have wavelength ranging for 10 to 500 kilometers, and wave periods can be up to an hour. So in the deep ocean, so okay, in this process we have overriding plate and subducting plate, and then when earthquake happen, we have displacement like that. Seawater displays, and because of the instability, the wave propagates. So in the deep ocean, the tsunami can travel as fast as a jet plane. So it can be in this presentation is 640 to 960 kilometers per hour. And so as you can see, now tsunami lifted, not yet, so still in deep water. So we can almost cannot see the amplitude. So as the tsunami leaves the deep water of the open ocean and travel into the shallower water, the tsunami transforms basically. The speed is slower, and consequently the height grows. Now here's some animation of inundation process, the coast. So this is first wave. First wave hit the coast, and we may have a throwback. So people will see the beach is kind of dry, but actually another wave coming in. So, and the second wave can be larger than the first wave in this animation. It's the second wave is larger, more destructive, and another drawback. And then we can have two, 3, 4 of wave. So it's not only one wave, not always only one wave. Well, this one is an animation for tsunami generation by a flank collapse during a volcanic eruption. Yeah, if an underwater eruption occurred, the hot magma can also create an explosion and also can generate tsunami. But this one is a flank collapse example. It's like landslide. Well, it's basically landslide. Again, well, this animation is the same. So just crossing the deep ocean. Okay, so here's just schematic of subduction zone. So we can see here in this diagram, we can see the mid-ocean ridge. Here we have convection current. So here plate 1 move to the left, plate 2 move to the right, and this plate, the plate number 2, subducted beneath the plate number 3, the continental plate. So here at the boundary, we may have magma rising because of the friction between these two plates, and it's generated volcanoes. So we have volcanoes around the subduction zone, which is true for Indonesia and Japan and South America. So that's why we have so many volcanoes in Indonesia. And as shown by the previous animation, if volcano is close enough to the ocean, it may generate tsunami during an eruption. Now here's a record of tsunami events generated by volcanoes from NOAA's NCEI database. I'm just going to zoom into Indonesia. So we have so many events in the Krakatau. So like the 1883 was Krakatau event, but after that it was Anak Krakatau, because the 1883 Krakatau eruption basically killed the volcano. And in 1930 or 1928, a new volcano emerged from the surface to the surface of the ocean. So then we named them Anak Krakatau. So here just showing the events and the years of the events. Okay, now here's some mechanism of, okay, some volcanic tsunami mechanism. Here we have underwater explosion, and then also blast by a shock wave. So it's also known as meteorological tsunami. And we also have some evidence of tsunami generated by pyroclastic flow. We can have pyroclastic flow with a dense pyroclastic flow, or I mean high density pyroclastic flow or low density pyroclastic flow. And we have probably caldera collapse can also generate tsunami. And the clear example was from the Anak Krakatau event. It was tsunami generated by subaerial failure of a flank collapse. So basically, according to Paris et al., this paper, there are at least 8 source mechanism, but in this presentation I will talk about maybe like 4. So I'm because I don't think we have enough time to talk about all of them, and I don't really have the capacity to talk some other source mechanism like air wave, lahar, or the other one, the collapse of lava. So I'm not really doing research for underwater explosion, but I did research from caldera subsidence and flank failure, and also earthquake associated with volcanic activities. The pyroclastic flow was something that I've read about, so I can explain those, and also underwater explosion. That's something that I haven't done. I mean, by myself, but I read papers on those source mechanisms. So first mechanism will be underwater explosion, and then continue by earthquake, and then pyroclastic flow, and finally the flank failure. Okay, now here's a source mechanism. So underwater explosion account for 25% of the events. And look from this table, the travel distance is not so far away, only less than 200 kilometers. So pyroclastic flow is account for 20% of the volcanic tsunami events, and travel distance less than 300 kilometers. Earthquakes, less than 20% of the events. The travel distance is less than 500. Flank failure, according to this table, I mean the 15% of it account for 15% of the events, and can travel up to 6,000 kilometers. And caldera subsidence, 10%, air wave 5%, lahar 5%, and collapse of lava bench is less than 1%. Now, underwater eruption, here's some example. There was a volcanic event in 1650. The name of volcano is Colombo. It's in Aegean Sea. According to this paper, the tsunami, well, we have two conflicting arguments here, basically. So according to this paper, the tsunami generated localized run-up as high as 15 meters and killed 20 people. But according to another publication, Nomiko, they suggested that small waves are likely to have been generated by the initial emergence of the Colombo volcano when explosion reached the surface, but may have been relatively small. So the tsunami, according to this paper, is small. Now here's an underwater eruption from Myojisho, Japan, during the period of 1952 to 1953. So it was begun on September 15. So because of the eruption, the eruption forming a new island, and then it was discovered by a fishing boat. And then after that, Japanese sent an oceanographic mission to investigate. Then the island disappeared completely again in September 23. But on September 23, eruption was observed and create a tsunami. Unfortunately, according to this report, the oceanic surface vessel was destroyed by the eruption, and then the sailor and the researcher were lost during that tragedy. It's located here, south. This is in the Izu Bonin Islands chain, so south of Japan. So this is Myojisho caldera, is over here. And of course, the Krakatau complex is the most complete, I mean, providing the most complete example of source mechanism. So they also have example of underwater eruption. Here's the explosive emergence of Anak Krakatau in Indonesia in 1927. The eruption produced tsunami up to 4 meters, according to this report. So in this is a map from that Geological Survey. So here's this line is the coastline before the 1883 event, before the 1883 eruption. And then this line is after the eruption. It was made in 1885. So the map before eruption was taken, well, sometime before that. But this map is dated on October 1883. So that is August, September. So 2 months after the event. The event was in August 1883. So you can see we have more lands. That's probably because of the maybe some materials from the eruption, just deposited there around the Verlaten Island and Lying Island. So here's the original coastline of Krakatau Mountain, and then after the eruption, we have, the eruption only left the remnant of Krakatau. This is called Rakata. We still have this. We can still see this Rakata Island. And then in the middle, we have Anak Krakatau emerging in 1927. So here's a research for underwater eruption. So here's just a schematic of experimental setup used to generate high pressure gas. This is from a recent publication by Shan. They tried to simulate tsunamis generated by underwater eruption in a water tank like this. This is just the dimension is like 1.5 meters, and width is almost 1 meter, something like this. And then basically air supplied from the cylinder to generate a maximum initial pressure of up to 1 kilopascal. And then we have a switch to release the compressed air here. And when it releases, we can see bubbles and water disturbance. And all of these were recorded by high-speed video camera. And then from this research, we can see this kind of result. So they tried different water depth and different pressure. So for this column, the water depth is 30 centimeter, 40 centimeter, 50 centimeter, and 60 centimeter. So become deeper and deeper. And here, this one is using 300 kilopascal. This one is lower pressure, 100 kilopascal. So if for 100 kilopascal, we have the blue lines is for the water boundary, and this is just bubble from the compressed air, the release compressed air. So you can see the water the amplitude of the water due to the explosion was become smaller and smaller for the deeper water. And this kind of shape, they call it dome, and this kind of shape, they call it finger. So we have different characteristic of explosion here. Okay, so yeah, they call this dome regime, and this is finger regime. So when the compressed water initially hit the surface, it would look like this, and then become bigger in B, and this is in the finger regime, it will splash out like that, and then it will come back, and then the water will propagate to the whole direction. So this is the sequence they found from their experiment. Quite useful. So yeah, they also trying to do, I think they haven't done the simulation yet. There's some simulation effort for underwater eruption. Maybe before we, but I cannot show you here, but because they haven't done it yet. So well, that is for eruption, underwater eruption. The next mechanism is earthquake. So before that, probably we'll have a break, or we'll have discussion, because it's already 38 minutes.